This is the fourth video for Unit 3, and it's about free body diagrams. What I want you to be able to do when you're done is to be able to analyze the forces on an object in mechanical equilibrium. We've had some practice at that. I want you to be able to use vectors to draw a free body diagram. And finally, I want you to be able to find the net force on an object using a free body diagram. The thing that I really like about doing this video is that it combines together a lot of the things that we've learned already. Be sure to take some notes for the video quiz that you'll have after this, and let's get started. The first thing we should do is define what a free body diagram is. And you've actually seen some, but we haven't called it a free body diagram yet. Those words have been on different things that you've looked at, like the FET forces computer activity that we did, but we've never formally called it a free body diagram. So what a free body diagram is this just a picture that shows all of the forces acting on an object, and it shows those forces as vectors. So here's an example that you've seen before, and it's a car moving, and this example was from the equilibrium video. So the eventual goal is that you'll be able to make free body diagrams, and that goal is going to come very soon. So what do you need to do to make a free body diagram? Well, first you need to draw the object. Now the drawing of this car is pretty complicated, so typically what you can do, instead of making a fancy drawing, is just draw the object as a dot. And then what you need to do is identify the forces and draw vectors to represent each force. So when we look at this car, what we see is that there's gravity pulling the car down, and that's weight. And then where the car touches the ground is at the tires, and so there's a normal force at each one of those. Then what we have is an applied force that's pushing the car forward, and a friction force that's pushing the car backwards. So now what we'd have to do is use a 6-in-1 to draw all of these forces. And then if you want to calculate net force, what you do is just combine all of the vectors to find the resultant. Now, this free body diagram is drawn very nicely. What you can see is that each of the normal forces from the tires is 1/4 of the size of the weight force, the force of gravity pulling down on the mass of the car. So these cancel each other out, the normal force and the force of gravity. Then there's an applied force that's pushing the car forward, and that's balanced out by an equal and opposite friction force pulling the car back, resisting the motion of the car. So, to determine the net force of this, and this should say sigma F for net force, we can have a resultant. Since the up and down cancel each other out, and the left and right cancel each other out, this net force is 0 newtons. So in other words, this car is in equilibrium. Since the car is moving, it's in dynamic equilibrium. Let's do some examples. So here's one. It says a 2-Newton apple is resting on a desk. Draw a free body diagram labeling each force vector with the correct symbol. What is the net force on the apple? So remember, step 1 was to draw the object, and instead of drawing a fancy object, you can just draw a dot. Then we need to identify each of the forces acting on the apple. In this case, we have a downward force from gravity that I'm going to draw in. And I'm using a 6-in-1 to make sure that the vectors represent the magnitude of the forces. So in this case, that's the gravitational force going down, and that's 2 newtons. And since it's resting on a desk, we're also going to have a normal force going up. And that's also going to be 2 newtons. So there's our free body diagram for the apple. It says, what is the net force on the apple? We have one vector pointing down, and it's 2 newtons, and one force vector pointing up, and it's 2 newtons. So the net force on the apple is 0 newtons. This apple is in equilibrium, and since it's sitting still, it's in static equilibrium. Let's look at another example. In this example, we're looking at a trapeze artist. The trapeze artist has a 450 Newton weight, and he's hanging upside down from a trapeze. Draw a free body diagram labeling each force vector with the correct symbol, and determine the net force on the trapeze artist. Okay, so what forces do we have here? Let's label those. Well, we have a gravitational force pulling that trapeze artist down. Then, what's keeping him up are these tension forces here. And since there's 2 ropes, there are 2 tension forces. So, step 1, draw the object. I'm going to draw it as a dot. There's a gravitational force of 450 newtons going down. I'm going to use my 6-in-1 to draw this. And there are 2 tension forces going up. And those are actually going to balance out the 450 newtons going down. So I want to make sure to draw each one only half the length of the gravitational force. And then I want to make sure to label them. Hopefully yours will look nicer than mine. 225. Then it says, what is the net force on the trapeze artist? Well, since the downward force is equal to the upward force, this is a 0 newtons. And he's just hanging there, so he's not moving. So that would mean that this trapeze artist is in static equilibrium. Let's look at our final example. In this one, we have a person pushing a box. The box is 2,000 newtons, and it's being pushed by a person who can't move the box, so we know that the box is at rest. They're pushing with a force of 500 newtons, but the box remains at rest. Draw a free body diagram labeling each force vector with the correct symbol. What is the net force on the box? Alright, so we've got to identify some forces. We said first, let's draw our object. Draw it as a dot. The forces acting on this: there's a gravitational force, the weight of the box. There's a normal force. There's an applied force, and that's the person pushing the box. And the reason they can't push the box is because there's a force going the opposite way, and that's the friction force. So, we have to account for all of these forces. And we want to make sure to use our 6-in-1 to make the forces representative of their magnitude. Alright, so first I'm going to draw in the gravitational force and the normal force. Here's the gravitational force of 2,000 newtons, and the normal force is equal and opposite, 2,000 newtons. Then I'm going to draw in the applied force and the friction force. They're 500 newtons, so they need to be only 1/4 of the length of the other two. So which is which? Well, the one pushing to the right is the applied force, and that's 500 newtons. And the one pushing to the left is the friction force, and that's also 500 newtons. Since the forces up and down balance each other out, and the forces left and right balance each other out, this sum of the forces, or the net force, is 0 newtons. Since this box is at rest, it's in dynamic equilibrium. Now these are going to get tougher as we work through some examples of free body diagrams. So tomorrow they'll get a little bit tougher. Today, jump right in, do the problem set, take this video quiz, and be sure to ask any questions if you're struggling with this.